Okay, so I believe that the screen is being shared. So we discussed quite a number of things yesterday, and we looked at the laws, the laws of sets. So we looked at those laws. So basically today what we'll be doing, we'll be going a step further to see first how we can verify. So what verifying basically looks at is, these are situations where they will give you a question where you have to solve the particular question in two ways. So for instance, you can be asked to use a particular maybe type of De Morgan's law. You solve the question using both types and then see if you get the same answer. So that means verifying, verifying that really the De Morgan's law holds true. And then the other example that we look at, we also look at the distributive law in the same context. So without wasting time, let's start. So example. So how the example will go will be, verify the following. Verify the following. So the set that we're going to be given, so we've got the union, one, 6, 7, 9 till 10. And then what we then have is set A. So set A is 1, 2, 3, 4, 5. Set B is 2, 3, 5, 7. And C is 3, 4, 5, 6, 7, 8. So now what we're going to do is we're trying to prove De Morgan's law. So you've been asked to first find what this is going to be and then verify that this is going to be equal to the equivalent of De Morgan's law, which is A complement union B complement. Okay, so since you are verifying, so what you're going to do at this point is you're going to first solve for the first one. So remember, this is different from proving. So what you're going to do, you're going to say, okay, so let me solve for A intersection B complement. So before you can solve for A intersection B complement, you first want to solve for what? A intersection B. So for A intersection B, let's just look at what we have here. So what we're going to have is, we are looking at things which are both in set A and in set B. And this is what? So when we check, we're going to see that it's what? 2, 3, and 5. Okay? So meaning our A intersection B is 2. Okay, let me just allow someone who's trying to join. Okay, so this means it's going to be 2, 3, 5. Then, so this is what our A intersection B is. So now we want to find the complement of this. So we look at our union. So A intersection B complement is going to be the universal set minus everything that's in A intersection B. So what we're basically going to do is we're going to write down the universal set, but removing the what? The elements that are found in A intersection B, because then that would be the what? That would be the A intersection B complement, isn't it? So what we are going to do now is to write this as, so remember our universal set is that one there. So we're going to write 1, then we're going to skip 2, 3, we're going to skip, then we're going to write 4, then we're going to skip 5, then we write 6, and then we can continue with 8, 9 and 10. So that's our answer. Now we're trying to verify, so we've found that answer using this one. So now let's use this and see if we'll get the same answer. Okay, now, so again, what are we going to find? You first have to find a complement and find B complement. So meaning for this particular kind of question, you want to solve what A complement is. So let's solve for A complement. Okay, so A complement is going to be, so let's see what our A complement is going to be. So A complement is, okay, so everything that's not in A but is in the universal set. So we're starting from 6 because 1 to 5 is in set A. So we're starting 6, 7, 8, 9 and 10. Then B complement, B is here, right? So it's starting from 2, 3. Okay, so meaning 1 is part of it, part of B complement. Then we go to 4, then 6, then we skip 7, we go now to 8, 9 and 10. Then what are we going to do? So here remember it's what? It's A union, it's A complement union. So what do? We just add these things. Let me just move this so that we can have space. So what we're going to have is 1, sorry, let me write that properly. So we're going to have 1, 4, 6, 7, 8, 9, 10. Remember that if things are repeating, you just have to write them once. So you see that from what we've written, okay, so let's just do this so we can be able to see what we've done. So you see that we found what? Same answer. So meaning we've verified the De Morgan's law. So that's how you want to go about it. So now the other law that we'll be verifying will be the distributive law. So let's use blue for this one. So okay, so for the distributive law, okay, so let's do that. Okay, so we're going to have A intersection B union C, which is equal to A intersection B union. Okay, let me just allow someone who's trying to join. Okay, so then we're going to have A intersection C. So now again, like what we did in the earlier example, we are going to solve using the first part and then using the second part and see if we can get the same answers. So now, so we're going to start with the first part like we did earlier on. So A intersection B union C. So to make things easier, you always want to start with what's in the brackets. So we know what's in the brackets here. What's in the brackets is B union C. So let's first find B union C. So to make it easier for everyone to follow through, let me just do this so we can be looking at the sets in question. That way, to be easier for you to follow through. So now we have that, and then we're going to say, so B union C, that's going to be 2, 3, 4, then that's going to be 5, 6, 7, and 8. Then remember it's A, then it's A intersection. So we first want to know what is A. A is 1, 2, 3, 4, 5. So we're then asking ourselves to say what is in B union C and what's in A. So we see that it's going to be 2, 3, 4, and 5, isn't it? So you see it's going to, so meaning A intersection B union C is equal to what? 2, 3, 4, and 5. So those are the elements that we have. Okay, so that's how we want to do that one. Okay, so let's see if we can create more space. Okay, so now let's now prove using the other method. So now the other method is, so we have A intersection B union A intersection C. So here, okay, let me just add some. Okay, so there we have A intersection B union A intersection C. So again, let me just do this so we can be able to look at the sets. So even as I'm answering, you can try to attempt and see if we are getting the same answers. Okay, so we're going to have A intersection B. It's going to be what? So that's what's in A and what's in B. So you see that will be 2, 3, and 5, isn't it? 2, 3, and 5. Then what's about A intersection C? That's what's in A and what's in C. So we're starting with 3. Okay, so that's 3 and 5. So that's what we are having, right? So since it's saying union, so therefore we're saying A union B, or A intersection B union A intersection C. So adding what we have above, so that's going to be 2. Oh, sorry, pardon me. A intersection C, there is 4 as well. So there should be 4 here. Sorry about that. Yeah. So it should be 3, 4, and that. Yeah. Those are the common ones. So you can see here there is 3 there, there is 4, there is 4 there, and there is 5, and there is 5 there. So yeah, so it's going to be 2, 3, 4, 5. So that's about it. Which when you see from where we started from, let me reduce this so that everyone can see. So you see that we found what? The same answers. So that's really how you, yeah, so you see this answer that we found here. It's the answer that we found here. So basically that's how you would verify them. That's how you would verify them. So now we can now move to the simplification of sets. Okay, so let me just give me a moment. Okay, so look at simplification of sets. So you remember what we discussed, that this is where you'll be given something that looks a little bit complex, but all that this requires from you is what? Application of set laws. application of set laws. Just that. If you're able to uh, apply these set laws appropriately, you shouldn't have challenges with this part. So then, now before I can proceed, there's something that I would like to explain, and what I would like to explain is this. Um, okay, it will be explained as we solve this question. So here is, so you have been told to simplify the following: A intersection B. Now these questions will always be in your tutorial sheets, tests, exams, because yeah, application of set laws. So when you look at a question like this, so first things first, you want to be able to understand the concepts and the things that you are dealing with. So A intersection B, I think we are all comfortable with that. But I think something that you'd have to be comfortable with is what this means. What A minus that means. So this is relative complement. You might remember what this means. We are looking for elements which are in A but not in B. So when you think about this critically, this is that. Remember that this can also be written as A forward slash B, just for your information. But this means the same as A intersection B complement. So all these are just the same things. So how does that relative complement make sense with this? Remember, you are saying what is in A but not in B. So what you are saying is basically what is A intersection B complement? What's that B complement? That B complement is going for the part where we are saying what's not in B. So already you are saying what's not in B. Then amongst the things which are not in B, okay, that's where then we want those things which are not in B. Okay, so after we've gotten those elements which are not in B, and then from those elements we want to find which of those particular elements are also found in set A. So you see that using that understanding, it basically pretty much means the same um, as what's in A but not in B. So here, so that's the first principle you have to apply here. So A intersection B union, then this one we change it to this. Now this is where you have to be very you have to be very careful. Okay, so okay, let me just check to ensure that people are there. Okay, find you're talking and people are not in. So now here is where you have to be very observant. So you see, you look at this, you look at this, and you look at this. What comes to your mind? I hope you are thinking of the distributive law. Huh? So you say, okay, so now what you're going to do now is you want to factor out A intersection. You're going to have B union B complement. Some lecturers will even be glad if you wrote here to say using distributive law. But it depends. Some may like it, some may not like it. So you want to inquire. But yeah, this is, but for me, I feel writing this is okay because they will know what you've done, right? And they will know that you just didn't copy from the next person. So, so is everyone clear with how we use the distributive law? In case you're not clear, ask. Okay, so we've used that concept. Now, what's the next step here? What other law are we going to use in this case? So now let's now look at this. When you look at this, remember we talked about the laws called complement laws. Complement laws. So using the complement law, which says if you've got the set and the union of its complement, you are getting the universal set, isn't it? So this is where I explained something where it's good. If you've got A union A complement, you get what? Universal set, isn't it? So that's what we are going to apply here. Okay, so that's the concept that we are going to apply here. So now, okay, let's use red. So now applying that, that's going to mean A intersection union. Okay, then at this point that we've reached, what law then are we going to use at this point that we've reached? So just to make sense of it, so this we've used the distributive law, then to break it down we've used the complement law. So that's just for you to understand, not necessarily that you have to draw these arrows, just for you to be able to follow through. Now, what principle then are we going to use to simplify this? Perhaps you might remember a principle that we called the, who remembers this? The identity law. So remember, what does the identity law say? So here we are using identity law. What does the identity law say? A union A, oh, A intersection union, it's A. If it's B union A intersection union, it's going to be what? Oh, sorry. A intersection universal set, okay, is equal to A. B intersection universal set is equal to B. So here we're using that identity law to say A union, sorry, A intersection union is equal to A. So you see what I was talking about, right? From this complex thing that we started with, we've just ended up with A. So that's how you use this. So that's why you remember me saying yesterday that these things have to be on your fingertips. Like you really, and not just memorizing them. I don't mean memorizing, but understanding them, because it's when you understand that you'll be able to answer these things. So that's really how you want to simplify that. So let's look at another example. So then I want to look at B. Our question B is, okay, so x intersection y, then there's complement outside the set, then you've got union, then you've got x minus y, then you've got complement. So how do you do this? So first things first, you want to get rid of the complement that's outside. And how are you going to do this? So you are going to distribute the complement. What law do we use to distribute a complement? Anyone that remembers what we discussed yesterday? What law do you use to distribute a complement?
Morgan's law.
Yes, exactly. So you want to distribute what? So there you're going to use the De Morgan's law. So basically, so here let's write using De Morgan's law. Using De Morgan's law. So using De Morgan's law, what are we going to do? So distributing. So remember, here we'll be treating these as entities. So we treat this as one, this as the union, and then we treat this as one. So distributing that complement to this, to everything in the bracket. The only thing that's going to be affected is what? Is that complement outside that bracket. So you've gotten rid of that complement, right? Then this union changes to intersection, isn't it? That's since De Morgan's law, if you recall, is if you're having something like this and then you distribute it, it's going to be like that, right? So that's really how De Morgan's law works. Okay, so just in case you forgot, that's how De Morgan's law is. So now Using that demograms, using that, so we now go to this other, the last part. So the last part is going to be x, that x minus y, which is this, that's relative complement, and then the complement goes there. So we've used the De Morgan's law there. So now at this point, what are we going to do? So okay, let's use black. So now at this point, remember what I said about what's in this set. When something is written like that, it can be tricky to understand. So what you're going to do is you want to rewrite it. And remember how we write this? We say x intersection y complement. So we've not distributed this, we've just rewritten it. Okay, as you might remember from the earlier example. So now what are we going to do? So you see this part, this part and this part don't give us problems, but the last part, oh my goodness, this is so complicated. So what do you want to do? Let's distribute that complement that's outside there. So let's distribute that complement that's outside. So how are we going to do it? We are going to use De Morgan's law again. So let's just write the first part like this. Now take note here, the De Morgan's law is just going to apply for things which are in the bracket. So what this means is when we distribute the De Morgan's law, that x is going to become x complement, that union, that intersection is going to become union, that y which was complement is just going to become y. Because remember, we looked at the complement law that says when you've got a complement then it's raised to another complement, it just gives the set, isn't it? So those are the complement laws. So remember that video was recorded, so go through these laws, ensure that they're on your fingertips because you need them. So once you've reached at this point, what you need now is analysis. So because there's a way we can simplify that, but it doesn't look obvious, right? So what you do is you want to draw Venn diagrams. You remember when we were looking at shading of sets, I said when it involves an intersection, at times shading may be what? Maybe the best way out of it. So we are going to shade the first set. So this is x, that, then that's going to be x and y, isn't it? So let's shade x intersection y. Okay, so x intersection y, that's that, isn't it? Then let's now write the second one, which is x complement universal y. So how do you shade that? So what's x complement? X complement, okay, let's write that. X complement is going to be what? Everything outside x. So let's shade everything outside x. Let's shade everything outside x. So once I've shaded everything outside x, and we said what does the union do? Union you just simply add. So then we add set y. So adding set y, notice when I'm adding set y, even this part, let me use a different color. Even this part, I'm going to shade it as well. Because it's part of what? It's part of y, isn't it? So eventually everything is shaded except what I'm going to put it to outline in green. So everything has been shaded except that part. So now when you look at these two diagrams, what parts have been shaded in this Venn diagram and in this Venn diagram? It's the intersection, isn't it? X intersection y. So that means here your answer is going to be what? X intersection y. And once it's at that point, there's nothing you can do to simplify it further, since you don't know what the actual elements are in x and y. But I bet you'd have simplified that as much as you can. So that's how you answer. So let's look at two other questions before we can really move to something else. But concerning sets, we just look at these last two examples. Then with practice, then you should be comfortable with sets. So let's look at C. Okay, let's use black. So this is B intersection A union B. So can someone tell me, oh sorry, I forgot something. There should be intersection here. So just by looking at this, just by looking at the way it's looking, what law do you feel is going to be helpful to us at this point? Just by looking at how the question appears, what law do you feel we are going to use just to ensure, just to ensure that this makes some sense? What law do you feel we are going to use? Please feel free to talk. Anyone? Yes? Anyone?
What are the distributive laws?
Yeah, exactly, right? Perfect. So we're going to use one of the distributive laws, huh? So that's what we're going to do, because just leaving it like this, I bet it's not going to do us any good. But when we distribute it, it's going to make sense. And how do you know that you have to distribute? Just by looking the fact that, remember, like I was explaining yesterday, the difference between the distributive and the associative law is that for the associative law, all the signs are going to be the same, right? But for the distributive law, you realize that usually when you want to use it, or even just when you're trying to look at it, you see that the signs are usually going to be different. What's in the bracket is going, the sign that's in the bracket is not going to be the same as the one that's outside. All right, so I explained that yesterday. So without wasting time, let's get into it. So here we write using distributive law. Using distributive law. So using distributive law, we're going to, okay. So using distributive law, we're going to distribute that. It's going to be B complement intersection A union B complement intersection B. Then here what we're going to have is, so there's not B complement intersection A, there's nothing we can do about it, but B complement intersection B. Can someone tell me the answer and what law you are getting it from? Okay, so in case you only know one, yeah, so you can just tell me what the answer is going to be, and if you can recall the actual law, then you can tell me. But yeah, if you just remember what the answer should be, you can tell me as well. That's fine. So for what's in the brackets there, what do you think should be? What do you think will be our answer here for this one? Huh? B complement intersection B. What do you think should be the answer? Just thinking about it logically. Yes? Anyone? Yes?
Going to choose the complement law,
Okay.
which says B intersection B should be equal to the universal set. So
B.
B complement intersection B should be equal to the universal set.
Okay. So you've got the idea right, but it's just that you've mixed them up, right? So remember it's B intersection. Oh, B intersection B. So sorry, let me go through that again. B complement intersection B is going to be an empty set, because you are saying what is in B and what's not in B, then you want to find what's common in them. It's an empty set, but however, I'm sure you know what you were talking about. Perhaps you just mix them up. However, the point that you mentioned was true, where you said B complement union B, that's a universal set. That makes sense, right? So you had the idea, you had everything. Perhaps it was just maybe when explaining that you made the mistake, right? So thank you very much for that. So this one, we know that B complement intersection B. You are saying what's in B and what's not in B. What's common in these sets? You don't expect anything. So this one is what? An empty set. Does it make sense? So now if you add this set union an empty set, it's just this set. Because any set added to an empty set is the set itself. So that's how you deal with that one. Because from there, there's pretty much nothing you can do to break it down further. So let's look at the last example. The last example is A complement union A intersection B complement. Okay. So this one looks interesting. So how are we going to go about this? So first things first, we've got a complement that's so you've got a complement that's outside. What do you want to do? You want to distribute it, isn't it? And we know that whenever you want to distribute a complement, which law do you use? De Morgan's law. So A and A complement, remember we said, remember those laws we are discussing, A raised to a complement again is going to be A, isn't it? Now, when I say A, it means that any other set, in case you think it just works for A. Okay, so in case you think it just works for A, when I say that, I mean general. So that's going to be A, and then this universal, this union changes to intersection. Then since this is in a bracket, or these are in brackets, they're going to be treated as one thing. So what we're going to do for this one is this. Okay, so there's a complement there. Okay, let me just show the complement properly so that we don't have challenges. Okay, so there's a complement there, and then the complement will just be outside. So the law that we've used is using De Morgan's law. So we've used what? De Morgan's law. Then again, this one again, we have to break it down further, right? So what we're going to do is, again, you want to distribute that complement. So you're only going to distribute it in the bracket. So A becomes A complement, intersection becomes union. Then the B complement raised to complement again becomes what? That. Okay, great. Now at this particular point, just by looking at this, which law do you think we are going to use next if we are to simplify this? Anyone? Please feel free to talk. The more you talk, the more you won't forget. Yes?
Distributive law.
Exactly, right? So remember, whenever you want to see if you can use a distributive, just think of, wait, is the sign that's outside and the sign inside, are they the same? If they are opposites, then I think, oh, okay, the distributive law can work here, either to expand or to factorize that particular set that you are dealing with. So here we're going to say, okay, let me write that bracket properly. It doesn't look neat. So we're going to say A intersection A complement union A intersection, am I making this mistake? A intersection B. A intersection B. So who can tell us the answer to the first to this? What's the answer? What's the answer? Please let's be quick. What's the answer there? Just for what's in the set, yes?
An empty set.
Yeah, so that's an empty set because we are saying, thank you very much, because we are saying,
An
yeah,
empty set.
exactly, thank you. So because we are saying what is in A and what's in A complement? That doesn't make sense, right? So it's an empty set. So we've got an empty set in union A intersection B. So if you're adding any set to an empty set, you get that set, isn't it? So you're getting your answer to be A intersection B. So maybe here I would like to highlight that I'm using. So here I'm using, okay, can you just give me a moment? Okay, so it's something that has happened to them. So what you want to indicate is you want to indicate, oh, at this point I used the what? I used the De Morgan's law, I used the this particular law. Yeah, that in that way you always be able to keep track of what you are doing. Okay, so just trying to check if everyone is in. So basically that's how you would deal with these kinds of things. So yeah, so there where we used the distributive law, you'd want to indicate, so actually there I used the distributive law. So having talked about those things, so we've discussed pretty much everything you have to know about sets. But again, the rest comes with what? Practice, right? So I'll try to check if I've got some tutorial sheets and I can be able to upload them on the Google Classroom so that you can be able to try the questions, and when you have questions, you can get back to me. Yeah. So having done that, so with sets, we are done basically. So now we're now going to go to the next topic, which is sets of numbers. So pretty much like sets. Okay, so let's here let me include using distributive law, so that when you'll be watching the video alone, you remember. Okay, so using distributive law. Okay, so remember using distributive law. Now we're now going to talk about sets of numbers. So there are about 2, 4, 6, 8, 9 sets of numbers that you should know and be comfortable with. So the first sets, so for this one, I would like it to be very interactive, because I think when one person is just talking, it gets boring. Huh? So I would want someone to think of, okay, so I'll just mention them and I would like someone to pick which one they will explain. So natural numbers, whole numbers, integers, rational numbers, irrational numbers, even numbers, odd numbers, real numbers, complex numbers. Again, I'll go through natural numbers, whole numbers, integers, rational numbers, irrational numbers, even numbers, odd numbers, real numbers, complex numbers. So whichever set of number that you want to talk about, the floor is open. Talk to us about it. Okay, so natural numbers. So what are natural numbers? So natural numbers, these are numbers that we use for counting. Okay, so let's say sets of numbers. So sets of numbers, these are, okay, so we've got natural numbers. So natural numbers, these are numbers that we use for counting. For instance, whenever you're starting to count, which number do you start from? You start from 1. Okay, under normal circumstances, you don't start counting from 0, isn't it? You start counting from 1. So these are counting numbers. These are numbers that we use when we are counting, right? So natural numbers, these are numbers we use for counting. That's the definition. So they start from where? They start from 1, 2, 3, and then they go up to infinity. Those are the 3 dots there. The second type of numbers are what? Whole numbers. So what whole numbers basically tell you is these are just natural numbers with 0 included. Okay, so whole numbers are just basically natural numbers, but then you're including 0. So what does this mean? Meaning these ones start from where? Start from 0. Okay, so that's something you have to be comfortable with. So let me just try to check to ensure that everyone is still in the meeting. Okay, so let's just So I'll be trying to reconnect everyone back in. Okay, so those are natural numbers. So those are natural numbers. So those are your natural numbers, whole numbers, and then we can now talk about integers. Okay, so we can now talk about integers. Okay. Okay, so now we can talk about integers. Okay, so I believe everyone is able to see my screen now. Yeah. Okay, so now since we've talked about those, so we've talked about whole numbers, let's now talk about integers.
I'm unable to see the screen.
Okay, and you're unable to see the screen. And how about now? You still can't see the screen? Okay, so okay, hopefully we'll be able to get the connection back as soon as possible. So integers, these are numbers where you're going to have zero. So integers is where you're going to have zero, positive and negative numbers. So those are your what? Those are your integers. Then when we talk about the rational numbers, now rational numbers, these are interesting because these are numbers which, okay, so I believe that everyone is able to see now. Everyone is able to see the screen. So so we've talked about integers, right? So integers, these are numbers which include, hello, you can't see the screen? Hello, yes.
No,
Okay, I'm not able to see the screen. Okay, so let me just stop sharing the screen and then start showing it again. That should help matters. Okay, so just confirm with me when the screen is able to show. Are you now able to see? Okay, just give me a moment. Yeah, so just confirm with me. So, uh, hello, can you now see? Okay, so when we talk about integers, so we are talking about numbers where these contain zero, positive and negative numbers. So set of integers is represented by z. So these are numbers where you have here you have negatives, then you have zero, then you have positives, like that. At times the same set of integers can also be written by others as 0, then plus or minus 1, plus or minus 2, etc. But the point is that you've got 0 and the positive and negative numbers. So that's just the hallmark principle of what? Or the hallmark feature of integers. Okay, you can now see the screen, right? Okay, so that's about it. So now when we talk about rational numbers, as I was saying, these are interesting because what we are going to say about rational numbers, these are numbers which can be written in the form of, so let's do this. So rational numbers, rational numbers. So this is rational, rational numbers. So rational numbers, these are numbers which can be written. First of all, they are represented by q, and they can be written in the form of m over n. Okay, so this is where m and n are members of integers. So what that basically means is that these m and n can be negatives, can be positives, and that. Okay, so that's important. But again, we know that n doesn't have to be 0, because you remember, if you divide any number by 0, you get what? Undefined, right? So we know that n shouldn't be 0. It can be any other number except 0. Now, one interesting thing about rational numbers is that they have terminating or repeating decimals. So what do we mean when we say they have terminating? They have terminating. So what it means terminating decimals is when you have something like 0.5.75, that's a terminating decimal. Why do we call it a terminating decimal? Because once that particular decimal ends, there is no way you can add it back. Okay, oh sorry, in short, that after that decimal point, after you have that 5. Okay, so let me just put that point so it can be clear. So if this is 0.5, so if this is 0.75, now with 0.75, that's what you call a terminating decimal, because there isn't anything that is what, there isn't anything that's recurring, like there isn't anything that's continuously and repeatedly uh, happening. So it's a terminating decimal. Then we are now going to get what we call repeating decimal. So terminating decimal is 0.5. Another example is 0.5, 0.375, and it ends, isn't it? But then when you have got a repeating decimal, these are numbers which are going to be written such as, so for instance, if it was 0.33333, perhaps you've seen such numbers on the calculator, so much that how you write them is you're going to write 0.3 and then you put a line on top to show that that 3 just keeps on going and going. Now, these concepts are very, very important, and when we talk about rational numbers in detail, which we'll do in a short while, you're going to understand that. So, what are irrational numbers? Irrational numbers, as the name entails, is just pretty much the opposite of what? Pretty much the opposite of rational numbers. So when you have irrational numbers, so these are all non non-terminating or non-repeating decimals. So remember the definition for the irrational numbers were, or rather was, that these will be either terminating or repeating decimals. But for irrational numbers, these are non-terminating or non-repeating decimals, and we'll discuss them in detail, because I'm sure you may have seen questions where you're asked to prove that this is an irrational number, or you have to prove that this is a rational number. So all those things are going to be discussed in great detail. So you want to be comfortable with that, but don't worry, it will have its own session. Then even numbers. So even numbers, we will know that these are numbers in which 2 can go in without leaving a remainder, isn't it? So same definition. So even number. So this is basically 2n, where n can be what? Can be an integer, or n is an element of integer, so it can be anything. So that's why even 0 is a what? 0 is an even number, and this is one thing that most people forget, because remember, n can be 0. 0 is an integer, so if you multiply 2 times 0, that's going to be what? 0. And 0 divided by 2, you get 0, right? So that's an even number. Okay, so please, whenever you are told to list something and it's talking about even numbers, don't forget 0. Most people forget and end up making mistakes. So we then want to talk now about odd numbers. So odd numbers is just pretty much like the opposite, right, of even numbers. Numbers where which are not divisible by 2. So odd numbers. So thinking about them, you would think them as either that, or you can think about them as 2n plus 1, and I'll explain what this means. So what this means is, for instance, if we've got a number such as 20, that's an even number, right? When you subtract 1, it becomes 19, which is an odd number. When you add 1, it becomes 21, which is a what? Which is an odd number. So that's what those 2 minus 1, 2n plus 1. So that's what it means, right? So that's important to take note of. So if this number for 20, even if it was 18, then you subtract 1, it will be 17, and the other side 19. So you see, those are your odd numbers. Then the last two classes, before we can look into rational numbers in more detail, so this is going to be real numbers. So real numbers represented by this symbol R with something behind. So this is just a combination of all rational or irrational numbers. So remember the definition of rational and irrational numbers? Now all those put together, those are real numbers. And this is where, when we talk about real numbers, that's why we'll be talking about the real number line. Okay? Remember that thing that we used to draw a long time ago? Yes, we'll be drawing it for sets as well. Oh, not sets per se, for real numbers. So it's very, very important to take note of that. Then the last set of numbers that we'll talk about before we talk, then after this, complex numbers, then we'll talk about sides, then we now start functions. So now, complex numbers. Complex numbers. So these are numbers which are where there will be like x plus I, then there is y, where x and y are real numbers. Okay, so I know this is not clear. Let me see what I can do about it. Okay, let's see. Okay, this is better. Okay, maybe let's just increase it more. Yeah, so what this means, okay, this is better. So this means y, okay, so x plus iy, where x and y are actually elements of real numbers. So how complex numbers are, they are like this. These are numbers where they have two parts. They have the real part and the imaginary part. So but we'll discuss this in more detail. So they've got the real part and the imaginary part. So the part which doesn't have the I, that's the real part. So for instance, if we've got 2 plus 3i, or I3, whichever. So, but you see that the one that doesn't have I, that's the real part. Then the other side part with I, that's the imaginary part. So basically, these are the groups of numbers that we'll be looking at. So the next time we meet, we'll be looking at rational and irrational numbers. How to prove that something is a rational number, and also by the same token, how to prove that something is an irrational number. So that's